Early on in the discussion of limits, we talked about ideas of indeterminate forms. So if you can reach back in your mind and think all the way back to when you were doing limits, indeterminate forms are sort of part and parcel for what you're doing. So examples of that you might remember is the so-called 0 over 0 or infinity over infinity case. So examples of that are things like sine of x over x as x approaches 0, or x squared plus 1 over 1 minus x cubed as x approaches infinity. And you recall that we discussed techniques on how to solve these two. We would use something called the squeeze theorem to solve this one, and we could factor that polynomial in a convenient way to do these types of limits. However, we don't really have the techniques to look at limits that look like this. If I took x as it approached 0 of this limit, if I plugged it in, I would just get 0 over 0, and I don't really have a good way to factor out an x or anything like that. So we don't have the techniques to discuss that or we haven't learned additional techniques even beyond what we're about to discuss that would allow us to meaningfully discuss this. And then the similar thing here with the natural log, it blows up almost immediately. You have a hard time dealing with these types of limits. But these aren't the only indeterminate forms. There are, in fact, I have 5 more here, but there are even more indeterminate forms. These 5 are these total 7 are some of the most common you're going to see. So not only do you have that, you have this 1 to the infinity. So this is a sort of a classical limit here. 1 plus 1 over x to the x. You notice if you take the inside limit, that term vanishes, but that term goes to infinity. So you sort of have to ask yourself the question, what's happening here? You know that 1 to a power is just 1, but is 1 to the infinity, is that really 1, or does the infinity drive it up, or does it come to some sort of equilibrium? How do you know? How do you know whether or not this thing spirals out to infinity faster than this thing shrinks down to 1? How do we do that? So we're going to have to learn some techniques on how to examine this. Another example is infinity to the 0. So if I do that, if I have infinity to the 0, well, we know that a number to the 0 power is 1, but is infinity to the 0 1? That's not really a meaningful concept. We know that this x goes to infinity, but we know that this exponent drives down to 0. Similarly, you have a 0 to the 0. So strictly speaking, 0 to the 0 is not defined. So if you take this limit, like this go from the right, this drives down to 0, and this goes to 0. So what's the actual limit there? How do we figure out what that number is? And the list goes on. We have infinity minus infinity. You have e to the x minus x. One of them's shooting off to positive infinity. One of them's shooting off to negative infinity. Which one wins? Do they actually cancel each other out? Is the answer 0? You don't know. These are indeterminate forms, just as we have this 0 times infinity. This, as x goes to infinity, this goes down to 0. 1 minus e to the 0 is 1 minus 1. So that's 0. That shoots off to positive infinity. How do we figure this out? So I'm talking a lot, and I'm just asking, how do we figure this out? How do we figure this out? And the answer is coming. We can use a series of techniques, one involving natural logs, because we know that the natural log is a continuous function, so we can sort of pass it through the limit, and we can kind of be clever and sort of assume that we have an answer. And the second one is this idea coming up that we're going to talk about called L'Hopital's rule, which relies on an extension of the mean value theorem, but the result is really interesting and quite elegant and allows us to solve limits, even like these right here, that took a little bit of cleverness before. We can zip straight to it by using the appropriate technique.